Everywhere we look, there seems to be a common pattern. Bigger animals have longer faces than smaller animals, especially when they're closely related species. So why exactly is this happening? Well, as luck would have it, a big literature review was just recently published that looks into exactly this question. A review written by me. In this video, I'm going to be breaking down the concept of Bite Force Allometry, which explains how the demands of bite force can dictate the proportions of the skull across a whole range of groups of animals. And at the end of the video, we'll look at some examples of where this applies. Dr. Rex here. Welcome to the Skullywag Lab, where I present the bare bones fundamentals of skull science. This is going to be a bit more of an advanced video, but I've had a few questions now about face length, so I guess we're ready for some more advanced stuff. So there's this pattern that we see in nature where bigger species in closely related groups of mammals tend to have longer faces. It's probably been known about for ages. The earliest mention of it I know of was back in the 1930s, but it was only formally recognised in 2013, and after that became known as craniofacial evolutionary allometry, or Crea. Now remember, allometry refers to patterns of shape change that occur with changes in size. And that's what we're talking about here. We're talking about size-related changes in skull proportions. Anyway, after that, a bunch of papers came out that recorded the Crea pattern in all sorts of groups of animals. This included groups like cats, ungulates, rodents, fruit bats, kangaroos, and even some birds. But you know what's funny? There was never a crystal clear explanation for why this was going on. One suggestion was that it might be a shift in the developmental timing of different parts of the skull that happens with increasing size. This was kind of related to the idea that larger species simply follow the natural growth of the skull seen in smaller species, kind of like becoming more physically mature adults. Another suggestion was that it might have been related to the negative allometry of the brain case, where larger species tend to have relatively smaller brains. See my video on what giants might look like for more about that. But you know what? These explanations would predict that all smaller species must therefore have shorter faces than bigger species. And this isn't the case. There's loads of small species with long faces, including bats, shrews, and some marsupials. The existence of these critters means that being small does not mean you have to have a short face. But a lot of small species do have short faces, and they often have larger relatives with longer faces. So what exactly is going on? Well, a more recent idea was that this pattern was something to do with equivalent function across the size ranges of these different groups of mammals. And this matched up really nicely with some earlier suggestions of a biomechanical relationship that hadn't really been explored too much. So Dr. Rex decided to explore this further alongside two of the biggest brains I know, Dr. Emma Sherritt and Associate Professor Vera Weisbecker. Well, the conclusion we came to is that this Crea pattern we see everywhere is likely often to be a product of three main things. One is how similar the skulls are that we're comparing. Two is how similar the biting and feeding behaviours are of the animals that they belong to. And three is the ways that bite force influences the evolution of skull proportions. So let's get into it. Let's start with species relations. Just how related the species involved need to be to have this Crea pattern seemed to vary a lot in the papers looking at it. Tests were being done on a whole bunch of mammal groups ranging from orders to genre, with a whole big range of divergence times as well. Instead, the pattern looked like it required the species involved to share a common skull architecture based on their evolutionary history. When species share a recognizable skull shape, this has been referred to as sharing an ordinal bow plan. For example, you wouldn't compare the skulls of dogs and cats because both groups are defined by a unique skull shape suited for their different modes of prey capture. By contrast, the giant panda has a skull with all the features of a bear, despite being secondarily adapted for eating plant material. So to start with, we need a common skull structure to work with. The next part of the story is how similar the feeding ecology or biting behaviours are between the species. There's another widely recognised pattern in nature where more closely related species tend to have more similar lifestyles and diets. This pattern is known as phylogenetic niche conservatism. Finally, let's look at how bite force influences skull shape. If you remember from my previous video, species that tend to bite harder often have more compact facial proportions. In other words, a more shorter, wider, or deeper skull. So we have these three things that we need to consider together. We have the common skull bow plan that comes from their evolutionary history. We have the more similar diets and feeding behaviors among more closely related species. And we have the effects of bite force on the evolution of the skull. And we argued that the way that these intertwine with each other across body size ranges in groups of animals is to do with several logical principles. Firstly, bite force is a product of muscle size and mechanical leverage. If you're not sure about what leverage is, check out that video in the top right. Secondly, all else being equal, muscles tend to increase in size with increasing body size. Seems pretty obvious? Thirdly, a species with low muscle force and high leverage will produce comparable bite forces to a species with high muscle force and low leverage. Taking all this together, all else being equal, a larger species with lower leverage can still produce similar bite forces to a smaller species with higher leverage. Now, because of phylogenetic niche conservatism, we know that more closely related species are biting into more similar foods or materials, so they probably use more similar bite forces to eat those similar foods. So maybe you're starting to see where I'm going with this now. Because bigger species can naturally have bigger jaw muscles, they don't need as much leverage. This can permit the evolution of a longer face. But smaller species need to retain more compact skull proportions. We called this effect Bite Force Allometry. And in most cases, reduced leverage in larger skulls involves the teeth being positioned further forward, which is exactly what we see in this animation of a small wallaby skull warping into a large wallaby skull. But just because you don't need a shorter face to bite hard, doesn't automatically mean you're going to evolve a longer face. No. There needs to be some kind of evolutionary incentive for the largest species of all these different animal groups to be evolving longer faces. Otherwise, it would just be better to have a short face and be able to bite into a greater variety of foods. So why would a longer face be beneficial? Well, that's the thing. It seems like having a longer face is beneficial for so many reasons, just not for biting hard. As one example, you can see my previous video on crocodile biting mechanics to see how a longer jaw can close shut faster than a shorter jaw. But there's tons of other advantages, including a wider gape, being able to reach further, fitting more food in the mouth, having room for bigger teeth, or housing a ridiculously long tongue. In some animals, it might even help for detecting predators. If the eyes are further from the ground while they're feeding, every microsecond counts, right? What this all means is that the need to bite into things is always a limiting factor in the evolution of other adaptations of the skull. And this limitation is going to be stronger in smaller animals because they need more leverage to bite the same kinds of foods. But Rex, I hear you say, there's so many examples of bigger species that still need to bite into harder foods than their smaller relatives, and they still have longer faces. So what gives? Well, to answer this, we need to look at the rates of change between size and bite force requirements. Check out this plot. The x-axis is how much more muscle force an animal can gain from being bigger. The y-axis is how much bite force is needed for the diet or biting behaviors of the animal, whichever bite force is harder, really. If the amount of bite force needed by a species matches how hard they can bite by simply being larger, there's no need to change the facial proportions. This would be called isometry, because the proportions don't change. But if a lower bite force is needed than what can be produced from increasing size, the face can be longer. A nice baseline for this pattern would be grazing species, because grass is really similar in composition, no matter what part of it's being eaten. This is why big grazers can tend to have really long faces. In fact, it's super rare for animals to have a nice clean distribution going above this line like this, because the resistance of foods rarely increases at a uniform rate. It usually seems to happen in jumps, where one species suddenly shoots up to this new threshold of bite force needed to bite into harder tissues or materials. We see this in shell-crushing otters, bone-cracking carnivores, and herbivores of thick resistant vegetation. And all these species have short, chunky faces that are very different from their relatives. So I'm sure throughout the course of this video, quite a few of you have come up with some obvious examples where this doesn't quite work. In fact, I expect to see some really good ones in the comments. And that's completely fine, because we're not claiming that this is everywhere. In fact, we argue against this being considered a biological rule in nature because of these obvious exceptions. This framework requires that bite force is a major selective pressure in the evolution of these groups of species. And there's plenty of examples where this just isn't the case. But what we are claiming here is that Bite Force Allometry is a frequent explanation for longer faces in larger species among groups that specifically share a skull-bow plan, have similar ecology, and where biting is a strong factor in their natural selection. So after taking all this in, let's do a quick test. I'll show you two animals, and you decide if you think Bite Force Allometry should be considered when comparing their skulls. A cat and a wolf. Both carnivores. The wolf is obviously bigger and has a longer face. Do we expect Bite Force Allometry to be a strong influence on the different lengths of their skulls? No, we shouldn't. They belong to different families, the Felidae and the Canidae, and have different skull-bow plans related to an evolutionary history involving different hunting techniques. How about a cat and a tiger then? The tiger is bigger and has longer skull proportions. Yep, we expect Bite Force Allometry to play a role here, because they are both of the family Felidae and have the same ordinal bow plan used for similar functions. Same dental formula and everything. A sea otter and a hog badger. Closely related, differences in face length are pretty obvious too. In this case, no, because they're similar in size and have very different diets. The hog badger sifts through the topsoil looking for grubs, while the otter can crush shellfish. A wallaby and a kangaroo. Yep, this is fine. Same ordinal bow plan, and similar bite force demands from their diets and feeding behaviours. How about a quoll and a Tasmanian devil? As members of the marsupial carnivore family called the Dasyuridae, they're closely related with a common skull-bow plan. The Tassie devil is larger, but it also has a wider face. For this instance, no. They might be both carnivores, sure, but the Tasmanian devil also incorporates bone cracking into its methods for obtaining food. And the ability to crack open bones means the Tassie devil has a super chunky head. You could almost think of it as a quoll hit by gamma radiation. Anyway, you might be wondering why this is even important in the first place. Well, when people compare the skulls of different species to look at adaptations to biting ability, they usually remove the effects of size to more directly compare the different skull shapes. But what Bite Force Allometry means is that size is an important part of how well an animal can bite, and shape and size should not necessarily always be isolated from each other for all kinds of questions. One thing we also note in the review is that one of the reasons larger body sizes might have evolved in a lot of groups of animals is because being released from this constraint of bite force might help the skulls become better adapted to other functions. And this was just recently supported in a paper published on deer species. So that's the Scullywag introduction to Bite Force Allometry. If you found this content insightful or interesting, leave a like and subscribe, and I'll catch you in the next video.